In this lecture, we'll be looking at moving average of order Q processes, or time series, usually referred to as MAQ processes. So first, let's refresh our memories on a MA1, or a moving average 1 process. Such a process is a weighted average of its previous white noise term plus a new white noise term. So recall our definition. For the MA1, we have YT differs from its mean today. Let's think of T on a daily time scale, although it can be on any time scale. Y differs from its mean today by some new noise term, and then we subtract theta times yesterday's noise term. So the memory in this process is in terms of the previous day's noise term. And these epsilons are a white noise process. So they're mean zero, variance sigma epsilon squared, and they are uncorrelated. So mu is the mean, theta was the weight for the previous noise term, and we saw in our lecture on MA1 processes that it didn't matter what value we had for mu or theta, your MA1 process was always weakly stationary. So it had a fixed mean and a fixed variance. We now expand this idea by, instead of just having memory for the previous day's noise term, we include memory for the noise terms Q days in the past. So we have the first day in the past, the second day in the past, down to the Qth day in the past. And each of those previous noise terms have a weight associated with them. Similarly to the case of the MA1, YT will be weakly stationary no matter what we choose for mu or the different theta values. And we will see that illustrated in just a moment when we look at the properties. So here's our defining equation for our MAQ process. And we see that mu is both the mean and the intercept of the process. We can see it's the mean if you take expectation of this expression, then the expectation of the left-hand side will be expectation of YT minus the expectation of mu. Expectation of mu is, of course, just mu because it's a constant, but on the right-hand side we'll have 0 because each one of these epsilon terms is a mean zero random variable, and so we end up with expectation of YT equals mu. The variance and the autocovariance will be more complicated, and they will depend on mu and the theta parameters. We'll get into that in a moment. But we also need to note an important property for an MAQ, and it is that this is not a regression model. So it's tempting to look at this and say, yes, we have a regression model here, where here is our response variable. We have some intercept. We have a new noise term, and then these epsilons are predictors. That is not the case, and the issue is that these epsilons are not observed. Think about how you work with time series data. You usually have a data time series. Let's say, right, so your YTs consist of Y1, Y2, Y3, up to YN. There are no epsilon observations here. All you're observing are these YTs. Because you're not observing the epsilons, you actually have to estimate them. So they're unobserved, and you need to estimate them using residuals when you actually do some type of fit for your time series. So when you're estimating using data, and you're estimating your mu and your thetas, at the same time, you have to be estimating what these epsilons are. Note this is quite a bit different than our ARP process, where we had yt minus mu was epsilon t plus phi1 times yt minus 1 minus mu up to phi p times yt minus p minus mu. We interpreted this as a regression, an autoregression, because you could interpret this yt as the response and these previous y's as the predictors. But you have the data for that. You have them in your given time series. This is very different. You, again, do not have these previous epsilon terms in your time series. You don't have any of them. You're not observing them. So they must be estimated. That makes the fitting of MAQ quite a bit more complicated than for ARP processes. That being said, you can compute your autocovariance function, and if we adopt the convention that theta 0 is equal to 1, this is what we get for our autocovariance function. And we see that, like the MA1, remember for an MA1, our gamma of h, if we say MA1, was 0 if our lag exceeded 1. Here, if our lag exceeds q, we have no autocorrelation. And it's the same kind of issue that this y sub t on its right-hand side has information that's embedded in the t minus 1, yt minus 1 term. This is embedded in the yt minus 2 term. This is embedded in the yt minus q term. But there's nothing of lag larger than q in this right-hand side. And so that results in a 0 autocovariance when you have two terms in your time series. Say we wrote it as like t plus q plus 1. These two cannot have any covariance. They have to have 0 covariance because this yt only has information from this part of the timeline. It doesn't have any information for lags, right? We're trying to draw this as this distance here in time is q. So anything that happened prior to q days in the past has no effect on the right-hand side, and that results in the 0 autocorrelation when you have a lag bigger than q. This can be computed by simply, again, using the definition of covariance and plugging in here. You would do your covariance of yt and yt plus h, the definition of our autocovariance function. And you can plug in, you can use equation 5 as is, and then you can use equation 5 with t replaced with t plus h and do your covariance calculation. And so you notice that this autocovariance depends on the variance of the white noise terms and the theta parameters. There is no time showing up in here. This is purely a function of h. Which means when you couple this with the fact that we have a constant mean and a constant variance, recalling that our variance is nothing more than our autocovariance at lag 0. So if you have h equals 0, your autocovariance is covariance of yt and yt, which is the variance of yt. And so we get this special case here, which is sigma epsilon squared times the sum theta 0 squared, theta 1 squared, to theta q squared, but note that in our convention, theta 0 is 1. If we divide our autocovariance function by this variance, we get the autocorrelation function. And so here we're doing that division. And the sigma epsilon squared, there's one in the numerator and one in the denominator that cancel, and this is the result. But again, we see 0 autocorrelation for lags larger than q, and non-zero autocorrelation for lags less than or equal to q in size. If we look at an example, this is a moving average of order 2 process. And so we see its defining equation here. So we have yt differs from its mean with a noise term for today, and then we have the noise terms for the previous 2 days with their own weights, theta 1 and theta 2 respectively. Using the result we just summarized on the previous page, our variance is our autocovariance at lag 0, or this expression. And we can then go through and apply our autocovariance formula. So let's recall what that formula was. So we had sigma epsilon squared sum I equals h to q, theta I minus h times theta I. So sigma epsilon squared sum I equals h. In this case, q was 2, theta I minus h, theta I. And we can see how that works. So when we have lag 1, and notice in this case, so h is equal to 1. And so we would have 2 terms, the sum from I equals 1 to 2. So we would have the first term would be theta 1 minus 1, or theta 0, times theta 1. So that gives us theta 1. Remember, theta 0 we're defining as 1. That gives us theta 1. And when I is equal to 2, we get theta I minus 1, 2 minus 1, or 1, times theta 2. We get that term here. For the lag of 2, we have h equals 2, so I goes from 2 to 2, so we'll have 1 term. And so we have theta 2 minus 2, or theta 0, times theta 2. And then we know, remember, this of course is for h in absolute value less than or equal to 2. When h in absolute value exceeds 2, we have no autocorrelation. So you can see this autocorrelation structure here, where you only have autocorrelation for 2 lags for this MA2 process. If we look at an example, just to put a picture and some numbers with this, this is an MA2 process where we have some memory. The first parameter we have 0.9, and the second parameter we have 0.7. We have a mean of 0. So we see here the defining equation for this MA2. So we're remembering 90% of the prior day's noise term and 70% of the noise term from 2 days prior. We see our autocorrelation function here. It drops to 0 once we hit lag 3. But we see about 66-67% autocorrelation at lag 1 and about 30% autocorrelation at lag 2. And when you look at the picture, the idea is that you see a little bit of clustering. So you can see how this is noisy, but there is some trend to it, and that's because you have this effect of the memory of the previous noise term. So you see how you have these little clumps that occur where things cluster together. And that's, again, because you're retaining these noise terms. So when you get a big noise term here, these next observations are remembering that big positive noise term. So this is the idea. And this can work for any natural number for a lag. You can have an MA30 if you want to. But the key thing to recognize is the defining characteristic of the MAQ is you're remembering portions of the Q previous day's noise terms. This is a very important type of process, and it's something that's going to help us build further if you watch future lectures when you want to build a robust class of models for the modeling of stationary time series.